Hi everyone, welcome back to the HoloTube. We're very happy today to have Carlos Hoyos from Oviedo, who will tell us about space-dependent symmetries and fractons. Please, Carlos, go ahead.
Okay, thanks a lot. Thanks for inviting me to talk here. It's great to be talking to the HoloTube crowd again. So I'm going to talk about some work that was made in collaboration with, well, one part of it was made with Kevin Grossman, Francisco Peña Benita, and Piotr Surovka. That will be the part about hydrodynamics that I will talk about. And there is another part that I will talk about with Ricardo Argurio, Daniel Nagels, and Daniele Musso. So this will be related to Goldstone bosons. And these two works, in principle, well, they originated with different motivations, and we're looking at different things, but they have in common these symmetries and fractons. So this will be the outline of the talk. So we'll first introduce a bit what kind of symmetries we are talking about and what are these fractons. Then I will discuss the hydrodynamics of systems with these kind of fractonic symmetries, so to call them. And then I will talk about the Goldstone bosons for broken translation invariance and how are they related to this topic. And I will conclude with some outlook. So let me start with the symmetries. So, well, first, what is a fracton? So in general, we can think of a fracton as some kind of excitation above the ground state with restricted mobility. And by this, I mean that it cannot move in all the spatial directions. So it can be completely immobile, it stays in place, or it can move along a line or a plane, if you're in more than 2 dimensions, but it cannot move in all directions. That will be the general characteristic of these fractons. So originally they were discussed in the context of some theoretical lattice models that people built, and there are some excitations that appear in these lattice models. So far, there is no realization in real materials of these lattices, but this opens some interesting questions in condensed matter phases. And then one can relate these fractons also to something which appears in solids, which are some defects that they can be of disclinations or dislocations. So these defects have this characteristic that they are immobile in some directions or in all directions. Okay, so they are just lattice defects. And then in general, we can think of a fracton as some kind of mode that has a dispersion relation, which is independent on momentum or on momentum in some direction. So you consider a profile of this mode, and it doesn't have dependence, the dispersion relation on momentum, the profile of this mode will remain the same always. No? So you can consider some localized profile and it will never move or disperse. So this could be some definition of the fracton. Now, this kind of excitation is related to some symmetries that depend on the spatial coordinates. Okay, so there are, well, the most commonly discussed one is the dipole symmetry, but I will talk also in some depth. Also, there are multiple symmetries, which are a generalization, or some other kind of systems that are called subsystem symmetries. So let me start with these subsystem symmetries. Okay, so I'm going to make a cartoon of how this subsystem symmetry is supposed to work. So imagine we have some kind of lattice that is represented here by these lines. So the lattice sites are at the crossings. And we put some degree of freedom at these lattice sites, for instance, a spin. And then we can consider a transformation where we rotate these spins. So we can rotate them all at once. No? So if we have a Hamiltonian, or if the energy, which is invariant under this transformation, or if the energy doesn't depend on what is the rotation, the global orientation of all the spins, then we say we can do we have a global symmetry, right? And then for this particular case, the parameter of the transformations is just some phase of U1 factor. So then if the ground state has all the spins pointing in some particular direction, then each of these transformations is taking us to another state with a different orientation, but the same energy. So that will mean that the volume of the space of vacuum will be given by the volume of the space spanned by these transformations. No? In this case, it will be S1. Now, imagine now a situation which is different. So instead of doing a global rotation of these spins, I do a rotation along one of these lines. Okay, so this will be, if we were in 3 dimensions, it could be a rotation on a plane, for instance. And I keep all the spins outside this line in the same state as they were before. So if the Hamiltonian is invariant under a transformation on a single line, then we call that a subsystem symmetry. Okay, and if all these lines are the same, then I can do these rotations on these lines, one independent of each other. So I will have as many possible transformations as lines I have in the lattice, or as planes I have in the lattice. So then in this case, that will mean that the space of vacuum is much larger than before. I have a U1 rotation for each of these lines. So I have as many as the size of the lattice in this direction. Now, in many cases in condensed matter, one can distinguish between different phases of matter by looking at the degeneracy of vacuum in some compact space. Now, for instance, topological states of matter with a mass gap, they have more than one vacuum if you put them in a torus, for instance. So one could argue then that this different size of the space of vacuum corresponds to a different phase of matter, if there is some phase that can be realized by this kind of lattice. Well, and this is what got interested many people in this Fracton study. Now, if we try to take the continuum limit of this lattice, so we make the number of sides go to infinity, or the number of these lines going to infinity, and we make the separation between these lines smaller and smaller, then this label that labels these lines becomes a coordinate. This will be the x direction. And then this discrete set of parameters become a continuous function of this coordinate. So in the continuum limit, we have a symmetry with a parameter that depends on the coordinate. So let me put you an example of a field theory model that will have this kind of subsystem symmetry, the continuum version. So this is a model that was studied in quite some detail by Cyber and Shaw. And well, it consists on an action for a free scalar with this funny looking kinetic term. So this breaks rotational invariance, and it contains one derivative in each direction acting on the field squared. So then there is a shift symmetry for this field where we can shift the field by an arbitrary function of x or an arbitrary function of y or both. So this has a subsystem symmetry for an x-dependent transformation and also for a y-dependent transformation. Now, one can look at the dispersion relation coming out from this action, and then it takes this form. So you see that if either qx or qy is 0, then we find that the frequency will be 0. No? So then if the configuration is constant in the x direction, for instance, qx is equal to 0, then it can have an arbitrary profile in the y direction. So it will become a localized mode in the y direction. No? And the same if we switch x and y. So I plot here how the dispersion relation for this mode looks like. is this funny looking surface that, as you see, this direction will be the frequency. So you see you have zero frequency along this line and along this line in the qx equals 0 and qy equals 0 directions. And then it raises up. And for comparison, I have put here the dispersion relation of a relativistic mode, which is a cone. So you see that in comparison, this has a single point where the frequency becomes 0, but this has two lines. So yeah, they're completely different. So we will see later on some dispersion relation that looks similar to the one of this model. Now, a possible classification of theories with subsystem symmetry that I stole from this paper of Katz and company will be the following. So you can have exotic field theories with these kinetic terms that break rotational invariance, like the previous model. You can have some other kind of theories which are called foliated field theories. So here you define some foliations along different directions of space, and you assign fields to these different foliations, and then you can work out the spectrum and find fractonic excitations. And there are yet another kind of theories, which I label here quiver theories. So here you can think of having a theory with many gates groups and fields transforming under these groups. So they form some kind of quiver lattice. And then if you're thinking about the field theory directions where the quiver is defined as some kind of space directions, then you can also find fractons in these kind of models. Okay, so I'm mostly going to discuss things related to these exotic field theories. Now, a question is that, do we need all this subsystem symmetry? No, this is a huge symmetry, depends on a continuous parameter, the coordinates. So can we find fractons in theories which are less symmetric, that they don't have this subsystem symmetry, they may have other symmetries, but you also have fractons. Now, one possibility is to consider a theory with dipole conservation. Okay, so let me explain this. So suppose you have a theory where there is some charge which is conserved, and you have charged particles. And then in addition to this charge, the dipole charge for these kind of particles is also conserved. So if you take one of these charges and you try to move it, then that will produce relatively a dipole. So this will be forbidden because then this wouldn't respect dipole conservation. What you can do is have two particles with opposite charges that have some dipole between them, and you can move them simultaneously in such a way that the dipole doesn't change. No? So then this means that if dipole charge is conserved, these single charges cannot move and they are fractons. Now, defining this rho as the charge density, no? The total charge will be the integral over space of this density, and the dipole charge will be the first moment of the charge density. Now you can ensure that these two are conserved, so the time derivative equals to 0 if there is no flux of charge or dipole charge in across the surface that surrounds some volume. If you modify the conservation equation of this density in this way. Okay, so the usual conservation equation is the time derivative of rho will be the divergence of a current, which is a vector, and that ensures that this is conserved. So now instead of that, you have two space derivatives of a tensor current. This, we will call it the dipole current. So with this structure, then this dipole charge is also conserved. You can integrate by parts, and then the time derivative is 0. Okay, so this will be the conservation equation for this kind of theory. Now, you can in principle couple these currents to gauge fields. So you can have the time component of the gauge field coupled to the density, and then you will need some tensor gauge potential coupled to this dipole current. No, and then the gauge transformations that correspond to the conservation of this current will take this form. So they're like the usual gauge transformations, except here you have two derivatives, except one. Now, the gauge invariant combinations that gives you the field strengths will be these ones. And then, although this in principle is, some purely theoretical construction, it turns out that you can find this kind of tensor gauge fields in some physical theories if you do some kind of particle vortex duality to the elasticity theory. If you do that in 2+1 dimensions, you end up finding these tensor gauge fields. And the charges, so this, what will be the fractons, corresponds to some kind of defects, the disclinations. And the dipoles corresponds to other kind of defects, which are the dislocations. Okay, so this was worked out in this paper originally. And this duality between these tensor gauge fields and these fractons and dipoles and defects has been generalized to other systems. They are all starting from the elasticity theory and adding more degrees of freedom, essentially. Now, we want to have an effective field theory that realizes this dipole symmetry. Okay, so the way to do this, if we are working with a scalar field, is the following. We have two possibilities. One is to try to do a linear realization. So, for instance, you take a complex field. The usual transformations associated to a scalar charge will be just a phase rotation, and you generalize it by adding a term which is linear in the coordinate. So this will be the dipole transformation. Or you could have a nonlinear realization where the usual transformation is a constant shift of the field. This will be a real field in this case. And you can generalize it by adding a term which is linear in the coordinate. So this will be the dipole transformation in this case. And these two can be related because if you consider this case and give an expectation value for this field, then it will be in a broken phase, and then the Goldstone boson will be the phase of this field that transforms in the same way as this. So you can in principle relate these two. Now, in the case of the nonlinear realization, the simplest action one can write will be of this form. So you can recognize this as some kind of Lipschitz. And then the dispersion relation is simply omega squared goes like cube to the 4. So in this case, the mode will be propagating in all the directions, and essentially there are no fractons. Okay. So this means that this dipole symmetry in this nonlinear realization doesn't imply there are fractons, at least if you consider just these fluctuations of the scalar. But you can check that the dipole conservation equation is satisfied because you can derive a word identity where you identify the density as the time derivative and the dipole current as these space derivatives of the field. Now, for the second possibility where we do the linear realization, then the dipole symmetry imposes some constraints on the form of the Lagrangian. So in particular, you can have terms that depend on the space derivatives, but they are all at least quartic. There are no quadratic terms. So if you do an expansion around the trivial vacuum where phi is equal to 0, to quadratic order, you just have time derivatives. So that means that the dispersion relation of this mode around this vacuum is just omega equal to 0. So this is a fracton. It's a completely localized mode. And that would fit with the charged particles not being able to move. Now, you can see here that there is an emergent subsystem symmetry because there are no space derivatives at the quadratic order. At the quadratic order, you can shift this field by an arbitrary function of the x and y coordinates. So in some sense, the dipole symmetry has imposed an emergent subsystem symmetry for the quadratic fluctuations, and that allows this fractonic dispersion relation. So we'll see later on something like this. Okay, so we will be interested in imposing this, introducing this dipole symmetry in hydrodynamics later. So let me talk a little bit about the algebra of the symmetries that we are interested in. So we are interested in space translations. Let's say the charge, the ordinary charge, which I call the monopole charge, and this dipole charge. And all the commutators are zero except for this one, which is between the translations and the dipole charge and is proportional to the monopole charge. So this looks like the Heisenberg algebra, no? Px equals 1. So this algebra can also be extended to add the spatial rotations, and is related to some non-relativistic algebras like the Galilean algebra or the Carroll algebra, where you take the Poincaré algebra and take the speed of light to infinity or to 0. Okay, so we call this the monopole dipole momentum algebra. I hope this name sticks. Okay, any question up to this point? No? Okay, so let me start discussing a little bit this hydrodynamics with dipole symmetry. So first, we want to look at this hydrodynamics because it might be relevant in some systems where you have these fractal excitations. For instance, I told you that you can have defects in solids that behave as fractons. And if you consider finite temperature, then you will start producing more of these fractons. Okay, so you start to populate these fractal excitations. And then you might expect that at long enough wavelengths, you may have a hydrodynamic description of this thermal state. Okay, so this is interesting, for instance, for these solids, where when you increase the temperature and you start producing more defects, until you reach a moment where you have so many defects that you destroy the crystal and then you melt the solid. No? So there is this phase transition driven by the defects. Now, because of the restricted mobility of these fractal excitations, the thermalization of the system is not completely obvious. First, that it will happen, and second, if it happens, it might take a very long time. Because, well, systems essentially cannot propagate as easily as in a normal, excitations cannot propagate as easily as in a normal system. Now, but, you know, modulo these caveats, then if we have a generic system with fractal excitations, we expect if we wait a long enough time, it will thermalize. We will have local thermal equilibrium, and then the hydrodynamic description will be appropriate. Now, according to the symmetry generators we have, we can consider different hydrodynamic theories. No? So if we just have the momentum and the monopole charge, this is the usual hydrodynamics. And then we just have the continuity equation for the current and the conservation of momentum with the usual hydrodynamic equations. We have the monopole and the dipole current, but not the translations. Then this is described by the dipole conservation that I showed you before. And then you can write a constitutive relation for the tensor current that involves two derivatives of the density. And then you find there are some diffusive modes, but instead of depending on the momentum squared, they depend on the momentum to the 4, the frequency. So this means that if you consider a distribution of charge, how the width is increasing with time, it increases more slowly than if you have ordinary diffusion. And then these modes are called subdiffusive modes. Okay, so this will be the effect of the dipole symmetry on hydrodynamics in this case. Now, if you add the space translations, then something new happens, which is before the commutator of the symmetries you had was vanishing, but now that's not true anymore. You have a non-zero commutator between the symmetries. Okay, so it might be that this produces something qualitatively different to these two previous cases. So that was our question. What happens if you add translations to this dipole and monopole charge? Okay, so the way, let's say, the path we took to find this dipole hydrodynamics was to use the Poisson bracket formalism. Okay, so this was pioneered by Landau a long time ago to do hydrodynamics, and it has been used later on in a similar context. Now, the idea of this is that first you take the densities associated to the conserved charges, and then you postulate some Poisson brackets for them. Okay, so these Poisson brackets are not arbitrary, but they're chosen in such a way that the charge associated to the momentum density will produce translations on these other densities. Okay, so these are fixed by symmetry. Now, you can derive the hydrodynamic equations from these Poisson brackets and from a Hamiltonian that depends on these conserved charges. Okay, and the dynamical equations will be just the time derivative of the charge densities will be given by the Poisson bracket with this Hamiltonian. Now here we make some assumption, which is that the dipole current or the dipole density is completely determined by the first moment of this density. Okay, you could have also considered having something like an intrinsic dipole density, and then you will have an extra density with an index. Okay, but we just consider the dipole coming from the first momentum of this density, so we don't have any more conserved charges. Now, if we write the Hamiltonian as a function of this charge density and momentum density, then we can consider the conjugate variables, the chemical potential and the velocities, and define a pressure, which is the Legendre transform with respect to these variables. Okay. And then when we derive the hydrodynamic equations from the Poisson brackets, we find for the density, this takes the usual form of the continuity equation. And then for the momentum density, with the help of this definition of the pressure, we find that simply the time derivative of the momentum density is the divariance of a stress tensor, which takes this form. Okay, so these two equations written in this way are completely universal. They don't depend on the form of this Hamiltonian or on the dipole symmetry. Now, so let me put you an example of how one can derive hydrodynamics from this. So suppose we take a Hamiltonian of this form. Okay, so this looks like the kinetic theorem of a non-relativistic particle, but divided by this density. And then we can extract the velocity as the derivative with respect to the momentum density. And that gives us this relation between the velocity and the momentum density. So this is precisely what you expect in a theory which is Galilean invariant. No? The momentum density is proportional to the current. Now, so this means that this form of the Hamiltonian is the one that corresponds to a Galilean invariant theory. Okay. So the symmetry is fixing the form of the Hamiltonian and the constitutive relations, but we still have the same equations as before. Now, if we substitute this inside the universal equations we had before, then we recover the usual Navier-Stokes and continuity equations of a Galilean invariant theory. Okay, so now the idea is to do the same thing, but with the dipole symmetry. So first, we have to realize that if we do a dipole transformation, the momentum density is not invariant, but it changes by a term proportional to the density. No, because the commutator of translations and dipole transformations doesn't commute. So instead of using the momentum density, it's convenient to make this combination where we divide by the density. So this is some kind of velocity field. And the variation of this velocity field is under a dipole transformation is that it's shifted by a constant. So now it's clear what we have to do to make things invariant under the dipole transformation. We have to construct a Hamiltonian that depends only on derivatives of this velocity. So the general form of the Hamiltonian will be this one. And now we can obtain the velocity by taking the variation with respect to the momentum density, and it takes this form. So the velocity will be a total derivative of this two-index object. Now, if we plug this back in the equations we derive from the Poisson brackets, we find that the equations of motion.
Carlos looks like a question. Alexander, just ask, you don't need to raise your hand.
Yeah.
What are your thermodynamic variables in this case? Is it still mu and v, or is it mu and jij?
So the variables are pi and rho. So the density and the momentum density.
Yeah, that's the conserved densities, but I mean, what are your thermodynamic variables that are conjugate? Like what are the quantities you do derivative expansion with respect to?
So I'm going to show a derivative expansion with respect to the density and this v. So I'm going to use the densities as thermodynamic variables in this derivation.
Oh, okay, so your pressure is defined still exactly the same?
Yeah, the pressure is the same.
Is it the dipole invariant, the pressure?
So the pressure will be dipole invariant in the sense that it depends only on these derivatives of this object. So then if you do a dipole transformation, it's invariant.
Oh, okay, thank you.
Yeah. Okay, so if we plug back these expressions in the hydrodynamic equations, we find that in fact, the hydrodynamic equations with the dipole symmetry, they are just the naive generalization of combining the situation where you don't have dipole symmetry and the situation where you don't have translations. So now the conservation equation takes the form of the one of a dipole current, where this dipole current is given by the symmetric part of this little j. And then the stress tensor takes this form. Okay, so in general, it's not a symmetric stress tensor. Okay, so to get a better idea of what kind of excitations we have with these hydrodynamics, what kind of hydrodynamic modes we have with these equations, let us consider some expansion in derivatives of the Hamiltonian. And then we write just up to second order in derivatives of the density and this capital B, which contains derivatives of the momentum density with coefficients that might depend on the density. So we will expand to linear order around some background density and zero momentum. Okay, so then the jij take this form, the pressure will take this form. And then we put it back in the equations. And then we can, for instance, take the divergence of this equation and take the time derivative of this one and replace from this equation into this one. So we end up with an equation for the density fluctuation, which takes this form. And well, this is just the equation for a mode with a propagating, which is propagating, and it has a dispersion relation where the frequency is proportional to the momentum square with some coefficient. Okay, so this means that in this case where, if you see here, I was imposing rotational invariance in all these tensor structures, then the mode is propagating, but this is a sound mode, But instead of having a dispersion relation which is linear in momentum, it has a dispersion relation which is quadratic in momentum. Okay, so that's the effect of the dipole symmetry. And if you consider more general Hamiltonians with broken rotational invariance, then you can have a more general dispersion relation. It will be still quartic in momentum, but you might have fractonic modes in that case, no? If this dispersion relation doesn't depend on momentum in some direction. Okay, so this I'm discussing is all for the ideal hydrodynamics. This can be extended to the non-ideal hydrodynamics, including the diffusive part, for instance, but qualitatively it's the same as I was telling you before. You will find subdiffusive modes. So let me summarize. From this Poisson bracket construction, what we see is that the conservation equations remain the same independently of whether you have the dipole symmetry or not, but the constitutive relations are modified. In particular, the continuity equation of the current is modified to have the form of a dipole current conservation. Now the dispersion relations are quadratic in the momentum for the propagating and the diffusive modes, and then we could have fractonic modes if we break rotational invariance. And then if we, instead of considering dipole symmetries, we consider multiple symmetries, we expect this to be similar, except this will be a higher power of momentum, essentially. Okay, so this will be the conclusions about this part. Okay, so I'm going now to change a little bit the topic, but we are still talking about these symmetries. We're going to talk about now emergent subsystem symmetries, and we saw already two examples in the talk. One was the model I showed you before with linearly realized dipole symmetry. We saw there was an emergent subsystem symmetry if we expand around the trivial vacuum. And in these last slides, I showed you the dispersion relation of the hydrodynamic modes. And I told you that if we break rotational invariance, in principle, we can have also fractonic modes. So that will correspond to having this emergent subsystem symmetry. Now, I'm going to explain some other examples where you have this emergent subsystem symmetry coming from the breaking of translation invariance. So our motivation originally was not to look for these subsystem symmetries or fractons. In fact, we were interested just in the what happens when you break simultaneously scale invariance and translation invariance. So what happens in particular, what kind of Goldstone bosons you have, how many, what are the dispersion relations. And we were motivated in part because there are some strongly coupled models of inhomogeneous systems using holography that combine this transformation of scale and translations. And so some people here work on these models. Now, when we have Poincare invariance, we know exactly how many Goldstones we have and that they have linear dispersion relations, thanks to the Goldstone theorem. But when Poincare invariance is broken, things are more complicated. And this is a topic that has been studied, especially for non-relativistic theories. There are theorems that tell you the dispersion relations and the number of Goldstone bosons. Also, when you break the symmetry with a chemical potential, then something interesting happens, that you have Goldstone bosons, but they have a mass, their gap, even though there is no explicit breaking. And the case we are interested in is when you break space-time symmetries, in particular translations. Now, this has been studied. No? I think everyone here knows that if you break conformal invariance, there is just one Goldstone, which is the dilaton, that you can think of as the Goldstone for the scale transformations, and then the rest of the special conformal transformations don't give you extra Goldstones. And part of this story is this so-called inverse Higgs mechanism, where you can solve for one Goldstone in terms of others. So this has been studied when conformal invariance is broken or when translations and rotations are broken, but not so much when everything is broken. So we don't know exactly in general how many Goldstones there are or what are the dispersion relations. Now, one thing we know, so if we have a system where, let's say, we break translations in some particular way. So what we do is we have a U1 symmetry, let's say, and we break translations and the U1 symmetry at the same time in such a way that we preserve some diagonal combination. Okay. Then there are some translations that can be completely unbroken, and there are some combination of translations and U1 transformation that is unbroken, and that allows you to have a state which is homogeneous. Well, in the sense that if you look at the effective theory, there is no explicit dependence on the coordinates. It looks like it's homogeneous even though translations have been broken. So the ground state of this system will be invariant under these translations and this combination of translations and U1 transformations. But both the U1 and the translations are broken. So if we apply this generator to one of these vacuum, it will produce, let's say, a Goldstone, or it will take us to another vacuum. Now, if we are in this situation, then dilatations must be spontaneously broken. Okay. So a way to see it is, let's say I have one of these vacuum and I apply the dilatation operator that creates, let's say, some kind of excitation. So this at zero momentum still is invariant under these unbroken translations. But if I apply this other unbroken diagonal translation, then what we see is that we don't end up in the same state. In fact, what we have is something like the U1 Goldstone acting on the original vacuum. So this means that this dilatation operator acting on the vacuum cannot give me the same vacuum. Okay, and in general, because of this, we expect that there will be some mixing between the U1 Goldstone and the Nambu-Goldstone mode associated to the broken scale transformations. And the mixing will be proportional to this parameter. Now, in order to describe this, we want to use, we will use a toy model. So we are inspired by the mean field description of spontaneous symmetry breaking. So if we just have ordinary spontaneous symmetry breaking, we will take the order parameter to be some field, and we'll write some effective action for this field, which is this Ginzburg-Landau model. So the potential will be such that the minimum is at a value at a point where this order parameter is non-zero. Now the usual story is that this coefficient A of the kinetic term will be negative, so this has the usual sign for a kinetic term. But if you do that, then if you have non-zero derivatives of the order parameter, that always increases the energy. So then you can never have a breaking of translation invariance if this is negative. So we will take this to be positive, so there can be a spontaneous breaking of translation invariance. And this is something that has been used in mean field descriptions of some inhomogeneous phases in QCD and condensed matter, like some inhomogeneous superconductors or other phases of QCD, like the chiral spiral. Okay, so we'll take inspiration from this. Now, the model we use is this one. So this is like a Mexican hat model, but for the space derivatives. No? You see the typical quartic potential. Now, the coefficient A that appeared before in front of the kinetic term is this one, and we choose it to be positive, so we have the wrong sign for the kinetic term. And we also make this a scale invariant. So this is why we have this field C here. This is to ensure that the system is scale invariant. And then if this term here has a zero coefficient, then there is a flat direction in this potential that corresponds to making the expectation value of this field equal to the these derivatives of the phi.
Sorry, can you explain again where you have two fields and what is
Yeah,
invariant?
so we have this field to, this is the field that will break spontaneously the U1 symmetry and the translations. So this is like the ordered parameter.
It's a complex scalar, no?
It's a complex scalar. And then, but if we want to have an action that looks like, that will have a minimum for non-zero derivatives, then that could be done just by taking this minus constant square, but that wouldn't be a scale invariant. So in order to have a scale invariant, we introduce this additional field. Okay, so this is like a spurion that restores the scale invariant of the model.
Okay, thanks.
Yeah. Now, we are looking for the ground states, so they have zero energy density with the action we wrote, and we are looking in particular to ground states that will give us a homogeneous action for the fluctuations. Okay, so we found two possibilities. One of them, we call it the helical superfluid. So this field is just constant. Phi is proportional to a plane wave. And then there is this relation between parameters in the Lagrangian and these amplitudes and the wave vector. Now this will fall into the class of models that are can describe charge or chiral density waves or a Q lattice. Now there are other possibilities to make this field, complex field, linear in the coordinates. That also works. We call this the metafluid. And this is similar to effective field theories for solids and supersolids that people have used in the past. So for the sake of time, I will just focus on the helical superfluid because we can also do more things with it. Now, the symmetries are the ones you expect. There is the U1 global symmetry for the scalar. If we make this lambda equal to 0, then there is also a complex if symmetry, and then we have scale transformations, spatial rotations, and translations. But notice that these two symmetries are not completely independent. We can either choose the phase rotation and the real shift, or the complex shift as the independent symmetries. Now, around the vacuum, we break the U1 global symmetry and the translations to the diagonal, as I was discussing before. And then we also break the shifts, the scale transformations, and the rotations. And then what we find is that around this vacuum, there are two gapless modes and one gap mode. Okay, but all three of them should correspond to Goldstones, even if one of them is gap, because there are no explicit break-ins. And we can actually relate them to word identities for the conserved currents. Now, looking at the quadratic action for the fluctuations, so I will expand the complex field in this way. So sigma is like the real part and chi is the imaginary part, and tau is the amplitude of the real field. So a combination of sigma and tau will be the dilaton, if you want. And then if you expand to quadratic order, you find this effective action. So you see that for chi, there are only derivatives depending on x, and for sigma, there are no space derivatives. Okay. And thanks to this, there is an emergent subsystem symmetry. There is also a dipole symmetry, which takes this form. So you see that in this subsystem symmetry, this function depends on both coordinates. So this means there is going to be a mode which is completely localized. And in fact, we find that indeed there is a mode which has omega squared equal to 0. And what is this mode depends on k. So if k is very small, k is going to 0, then to keep this finite, we should scale beta by k. So this will kill this term in chi. So this means the fracton, which is immobile, will be sigma. But because we have this subsystem symmetry, this means that chi will be completely localized in the y direction. So actually chi is another type of fracton called a linear with a dispersion relation that depends only on qx. We take the opposite limit, then this drops from sigma. And well, this alpha doesn't do anything more than this beta, so chi becomes the only fractal in this other limit. Okay, so there is always a fracton with omega equal to 0, but what is it and how the other models behave? How the other models behave depends on k, or the relative size of k with respect to the spatial momentum. Now, we can add a chemical potential to this model. That means adding a time-dependent phase for the complex scalar. This will make the ground state will be unstable unless we add this other term here. Okay, so in order to do this, we need to add this lambda to make it different from 0. And then the amplitude of the complex scalar is fixed by the chemical potential. But still you find some kind of fracton, but the dispersion relation is modified in some more or less complicated way. If Qx is equal to 0, you still have that omega is equal to 0. And in fact, for a small momentum, you find that the dispersion relation is proportional to this. Okay, so for Qx equal to 0, omega is equal to 0. But if the Qx momentum is very large, then you find something which is an immobile fracton, but gap. And the gap is proportional to the chemical potential. Okay, so there is no dependence on momentum when the momentum is very large, but the mode is gap. So that's the effect of the chemical potential. And then finally, we look at modifications of the action. We took a very spatial action, this Mexican hat, so you can add more higher derivative terms, like this one. We studied others as well, but the qualitative, to this order in derivatives, that doesn't change qualitatively the result. And what this term is doing is adding a new term in the action, which involves a derivative with respect to y of sigma. Okay, so before sigma didn't have any space derivatives in the quadratic action. Now it has this term. And this modifies again the fracton dispersion relation, which becomes now some kind of non-analytic dispersion relation. So at low momentum, it takes this form. So here I just want to point out this factor here, which is the same as the one we saw in the first model, no? The Cyber-Sao model, where we have this Qx squared times Qy squared. No? So we expect the dispersion relation to look more or less similar to that model. Now, and finally, we can add this deformation and also chemical potential. So here,
you had higher derivatives before, but the dispersion relation was still analytical. Only when you add the like 6 or no 4 or what? What is?
So we originally have this term, which is 4th order in derivatives,
and then everything is still analytic.
And then it's everything is analytic, yeah.
And now you add also something that is also 4, no?
Yeah, this one.
But this changes.
Yeah, the mode that was omega equals to 0 before becomes this funny thing.
Mm-hmm. Okay.
So, okay, so I'm plotting here the dispersion relations in all the cases, so you can see it more visually. So no deformation and 0 chemical potential is just the fracton with omega equal to 0. And then if we have a chemical potential, then if Qx equal to 0, then omega is still 0. But if Qx is non-zero, then the dispersion relation is lifted. Okay, so then it becomes, there is some propagating mode when Qx is different than 0. The deformation, if there is no chemical potential, it introduces this dispersion relation, which is, you recognize here that if Qx or Qy is 0, omega is equal to 0. So this is the same as the Cyber-Sao. And then outside these lines, then you have a dispersion relation that looks more or less similar. And the chemical potential is lifting, again, the dispersion relation along this axis. Okay, so this is the effect of both the deformation and the chemical potential on the fracton. Okay, so let me summarize. So the takeaways of all this discussion is that we can find these subsystem symmetries or these multipolar symmetries as emergent symmetries in the low energy effective theory of these models with broken translation invariance. Okay, so this is an infrared symmetry rather than the UV symmetry that you have in the lattice models, no? That appears when you consider things localized on one plane in the lattice. No? That's very UV. Now, this also tells us that you don't need exact dipole or subsystem symmetries to have fractonic dispersion relations. But of course, all I have said here is, mean field and looking at just quadratic order in the action of the fluctuations. No? So if we go beyond that, if we consider the effect of the fluctuations, then this may change. No? Because, well, first of all, because these dispersion relations are typically higher order in momentum, then the infrared divergence are expected to be worse. No? So it could be that, for instance, they will kill completely the vacuum with a spontaneous breaking, or they can modify the dispersion relations in other ways if you go beyond these approximations. Okay, so this is something one has to look at. Okay, so that will be the end of the discussion. So I have a couple of minutes, so just let me say very briefly possible future directions related to these symmetries and fractons. So first, we're in Hall of Youth, so we shall talk about holographic models. So one may wonder how to realize these multiple or subsystem symmetries in strongly coupled theories using holography. So I only know this work related to that, which is a quite involved model, but maybe there is a simpler way to realize these kind of things. Now, there is a general question of, I've talked a little bit that when you break a spatial symmetries, like translations, then there is no general theorem that tells you how many Goldstones you have or the dispersion relations. And you can extend that to other coordinate dependent symmetries like these dipole or multipolar symmetries. So the question that you had for the translations and these symmetries extends also to these multipolar symmetries. So this is something which is also an open question. And now related to this fractal elasticity duality. So when I discuss these tensor gauge fields and that the defects appear as fractons, they're always treated as external sources, these fractons. So it's like the dynamical fields are the tensor gauge fields, and you see how they behave in the presence of these external sources, which are the defects. But it will be interesting, I think, to have some effective description of these defects that allow you to describe their dynamics together with the dynamics of the elastic fields. Yeah, so that was all I wanted to tell you today. So thanks for listening.
Thank you, Carlos. Very nice, very illustrative. We had time for questions. I see a lot of people here, so we should have questions. Please don't be shy.
So could you go back to slide 16, I think it was? When you...
This one?
Yeah, exactly. So you say this definition of pressure as like a Legendre transform of H with respect to rho and P still holds for the fractonic hydrodynamics. But H is invariant, and everything else is invariant, but P is not, the momentum. So clearly the pressure is not invariant.
Yeah, I guess you're right. The pressure will be shifted by the dipole transformation. Yeah. And
then in the constitutive relations that you wrote for Tij and Jij, I think it was slide 19. Yeah, here. So I think I was expecting to see something like a derivative expansion with respect to rho and p. But here I see like it looks like an expansion in. I mean, it doesn't really look like an expansion because there is no p. Jij is not just a function of rho and p.
Well, it's an expansion. There are two expansions. One, I'm expanding the Hamiltonian in derivatives, so up to quadratic order.
No, I'm talking about constitutive relations. So I'm talking about the derivative, about the derivative expansion of your macroscopic currents, which is Jij and Tij.
Yeah, but what I'm saying is I can derive the constitutive relations from the Hamiltonian using the Poisson brackets. No? So in this formalism, essentially, once you define this function, then you can find the form of the current is determined by this VI. No? VI is the derivative of H with respect to PI. And the pressure or the chemical potential is determined by the derivative with respect to rho. So once you have the Hamiltonian, the constitutive relations are given.
But you have a different Hamiltonian now.
Yes, I'm writing a Hamiltonian, which is invariant under the dipole symmetry and expanded up to 2 orders in derivatives of the VI and the rho.
So this Hamiltonian that you write here is not a function of P. It's a function of the gradient.
It's a function of P through V, through capital V. And this capital V is the momentum density over the charge density. So in order for this Hamiltonian to be invariant and the dipole transformation, it must depend only on derivatives of this capital V.
So it depends on the derivatives of the momentum.
It depends on the derivatives of the momentum, yes.
So it doesn't depend linearly on momentum. Like it's not.
So if you take the derivative with respect to V, if you take the derivative of this function, of this VI, you'll have a term which is P times derivative of rho. So it depends on derivatives of P and on P, but always in these combinations.
Okay, thank you. But because it seems to me like this expanding those Jij and Tij by standard ways of hydrodynamics doesn't really work here, because you have because if you can just say I don't know Poisson brackets and I just expand in terms of my conserved densities, my macroscopic currents, and it seems that wouldn't work.
Yeah. So one thing I'm doing. So one thing here is that everything I'm doing here is for the ideal fluid. Okay, I'm not adding dissipative terms in this discussion. So these derivative terms appear at the ideal order. Okay, they are not like when you write the fixed law for the current to find the diffusive mode. So this is just at the ideal order. You already need to have derivative terms. Okay, so then you can add dissipative terms to these currents using this derivative expansion that you said. But that was done later on by these people.
And so your momentum, stress momentum tensor is not invariant on the dipole because it depends on pressure. So it transforms.
Yeah, but it also depends on V. So I think probably these two compensate.
Oh, okay, yeah, okay, thank you.
Okay.
Rene has a question, please. Just.
Hi, Carlos. Nice talk. Thanks a lot.
Thanks.
So my question was, so the theory you've shown in the beginning had these higher derivative kinetic terms. Is it always necessary that these theories involve higher derivatives, or can you imagine some two derivative theory?
This one?
Yeah, that has these fracton symmetries.
Yeah, you could have a theory where you just have a derivative with respect to x, right? And that will have a subsystem symmetry, which is as if by a function of y. So yeah, that could be a possible theory, just with two
So there are
derivative terms.
examples. Okay, yeah.
You can even consider a theory with just one derivative terms, like a chiral boson.
Okay,
So,
yeah.
So it doesn't have to be higher derivative.
Yeah. Okay, thanks. And the second question, so you said this this dipole theory basically relates to the theory of dislocations and disclinations. Is there any relation to torsion / spin as a conserved quantity with these in these dipole theories? Because we know that dislocations give rise to these Burgers vectors, and these Burgers vectors give rise to torsion for the electrons and that propagate in this lattice. So there should be some close relation between these theories and, let's say, spin-full hydrodynamics. Or...
Yes, so the torsion part is the non-dynamical part in this discussion. So you have these defects, they produce torsion. So the torsion, okay, if you're in the elasticity theory, no, and you're working with the displacement field, the torsion comes from singular configurations of the displacement field. They're like vortices of the displacement. And yeah, so that part will be like these fracton and dipole charges that are not dynamical in this discussion. So these tensor gauge fields couple to these charges. So they couple to the torsion.
Okay. Yeah. Thanks.
Yeah. Thanks.
More questions? Come on. Don't be shy, please ask questions. I will then shut off the recording and ask for informal questions again, but
maybe I can ask another question then. So it's also not necessary to break relativistic invariance, right? I mean, I'm thinking about these higher form symmetries that you also have in string theory, for example.
Well, I'm not sure.
I mean, here you broke relativistic invariance, right?
Yeah. But you mean to have subsystem symmetries, or?
Yeah. Yeah, I mean, subsystem symmetries, you probably always have to break relativistic symmetry, right? Because it's a subsystem, so there's some boosts and some rotations always broken. In that sense, in that sense, you always have to break some part of the relativistic symmetry. Yeah,
I think, well, at least this form of the equation for the dipole symmetry is not relativistic invariant, I think. So
yeah.
So then if there is a version which will be relativistic.
Well, I mean, if you think about string theory, right, you have D branes and they source these higher form gauge fields, and of course you always break some part of the full relativistic invariance unless you have the top form, but then that's Poincare dual to a scalar, basically, right?
Yeah, but in principle, the higher form doesn't mean you have an immobile object.
No, even if they're mobile, it's just like you have these charges around.
Yeah, that will be like a higher dimensional object coupled to the to that. But here, notice that this is not like a form symmetry because this is a symmetric tensor.
Yeah, this is not exactly the same. Yeah. Okay.
Thanks, Rene. No more questions? I should play this game of like just remaining silent to make people. Somebody did that here for like 1 minute until somebody. but
Yeah,
I guess I'm not patient enough.
then yeah, if you're the chairman, you have to prepare a couple of questions in case somebody else, nobody
No,
else.
but there's been questions. Come on, I'm just seeing that there's a lot of people here who knows a lot about this, and I don't want to ask my students. No, but what I will do now, if there's no more questions, is stop the recording and then ask again to see if there are less formal questions. Okay, so before stopping the record, let us thank Carlos again. Very nice talk. It's been nice to have him here. And I in place you for like next week we meet again on Tuesday for, I think it's Derek Tini talking here on Holotube. So see you all.